So, very good morning to all the participants, both online and offline, and welcome you all to the fourth day of this GIAN course titled Thermochemical Conversion of Biomass Waste to Bioenergy and Value-Added Products. And today our first session will be delivered by Dr. Remya Nilanchari. She is currently working as an associate professor in School of Infrastructure, IIT Bhubaneswar, and with her expertise in microwave technology for solid waste management, advanced oxidation process for water and wastewater treatment, and development and characterization of novel nano catalysts for different treatment purposes. She have many research journal papers in various reputed journals and publications. Along with, she is an active member of various research bodies like American Society of Civil Engineers, Asia Pacific Chemical, Biological and Environmental Engineering, and American Chemical Society, and so on. And she is also an editor for series of books titled Agricultural Waste to Value Added Products and entitled to many awards, namely Innovation Award in National Green Charcoal Hackathon India, Outstanding Women in Research, and Outstanding Women in Engineering Award, Women Researcher Award, Golden Bamboo Scholarship, and many mobility and research grants are a few to name. With this very brief introduction, I would request Dr. Iman Ilanchari for carrying on this session. Thank you.
Thank you. Am I audible? So welcome to the fourth day of this course. And for this first session, we'll be dealing with the microwave copyrolysis of commingled waste or mixed waste to value-added products or biofuels. So before going into the topic, as we are aware, we have the new solid waste management amendment in India. It came in December 2024. So what is the new thing that is present in this amendment? If you see, the segregation of waste. Though we are saying the waste to be segregated, because we don't have a single treatment practice to cater different types of waste, right? And most of the time, the waste treatment facility is facing issue in segregation, and which is consuming lot of the operating cost in waste management facility. So in these new amendments, we have to segregate the waste from source, and it is the responsibility of the waste generated to segregate at least into two categories, that is wet waste and dry waste, or biodegradable waste and non-biodegradable waste. And coming to the other aspect of the latest amendment, we have to prevent mass burning of crop residues, agricultural residues, right? We are aware that again the Delhi pollution, always we are talking about the pollution in our capital city, and we are thinking that the credit goes to the vehicular pollution, but study says the main cause of pollution, air pollution in Delhi, is due to the crop burning in northern states, right? So the new amendment take into consideration again preventing the agricultural burning, mass burning of crop residues post cultivation. So who is responsible for practicing these new guidelines? No one is exempted from this, because you can see the list: urban and rural bodies, state and central government organizations, all domestic, institutional and commercial sectors. So the waste segregation has to be practiced from each sector of waste generation. And of course, we are excluding the hazardous or radioactive waste because it is catered by a different rules and guidelines. Now with this latest amendment and advancement in solid waste management rule, we are focusing at proper waste management with circular economy in place. Because in earlier days, we used to think of disposing of the waste so that it is not harmful to the environment, right? So it was more focused on linear economy, waste generation at the source, treatment and disposal, right? Now we have to reduce that disposal part, landfilling of the waste even after treatment, and we are trying to include the circular economy concept so that we can generate some revenue out of waste. So you might have heard so many terms: waste to wealth, waste to energy, trash to cash, right? Because we have to implement that circular economy and gain some revenue out of waste instead of just disposing it into land. And more strengthening will be coming in monetary aspect for penalizing the defaulters. And no sector is excluded. It is not, waste management is not only the responsibility of urban sectors. We have to look into the rural area as well to cater the overall improvement in environmental quality. So all of us are responsible for waste segregation from source, and as a waste management engineers, we are responsible for implementing circular economy in waste management. Now, what is the need of MSW management? So this is just a different fraction of solid waste, component of solid waste in a global perspective and as far as India is concerned. So if you see the different categories of waste from source, in a global perspective, food waste is more or less 44%, and we are also close to that. 50% of the category of generated waste in India is food waste, garden trimming, or other biodegradable waste. So you can say 50% of the waste, either in the global scenario or from India, is biodegradable. And the remaining portion, if you see plastics, clothes, paper, right? These can also be converted to useful product. And whenever possible, we have to incorporate that R concept. How many R's are there in solid waste management rule at present? 3, 4, 5. So reduce, the best option. Reuse, if not reduce, reuse. Recycle, regenerate, repurpose. So we are adding so many R's to it so that none of this waste is going to landfill or waste value to be generated out of waste. The main issue is, so in earlier days, the waste generation was less. We were having ample land area to dispose of the waste, right? But if you see with increase in population, the population increase, so is the industrialization. So we can expect that the waste generation per capita is increasing day by day. And if waste generation is increasing, of course, the land requirement for the waste management is also increasing, right? So in earlier days, the waste management was mostly focusing on volume reduction. Volume reduction in the sense we are removing the moisture content for volume reduction and disposing of this into land. This may not be practical with increase in population, increasing waste, and decrease in land availability. And coming to the other aspect, the use of fossil fuel. So advancement in, say, vehicular transport, industrialization is demanding more and more requirement of fossil fuel with respect to coming years. And if you see the fossil fuel reserve left, as per the study in 2019, so we are around 5 years ahead from this study. So even this study says the maximum coal reserve is up to 100 years, and natural gas and oil reserve is for less than 50 years. But we cannot think of a life without coal or fossil fuels. What if the reserve is no more? So we have to always think of an alternate coal or fossil fuel. But where is the source? Naturally, to generate the fossil fuel, it takes millions of years. So let us think of our waste to be converted to an alternate fuel, either solid or liquid residue. So this is the waste generation. The predicted waste generation in a global average by 2050 is around 3.4 billion tons. So if you see the current scenario in India, we have around 62 million tons of waste generated per year, averaging to around 1 kg of waste generated per person per day, right? And most of this waste collection is not done, and from the collected waste, around 90% is only treated. So by keeping into account the less land availability, more waste generation, depletion of fossil fuel reserve. Let us think of the opportunity for waste to energy conversion from the ample source of resource, that is the waste generated from different parts of the world. Now, if you need to convert waste to energy, especially through thermochemical conversion techniques, it has to meet certain criteria. So as per the rule, it says non-recyclable. So as I mentioned, we have to go for reduce, reuse, recycle if not. So if the 3R fails, the rest non-recyclable part of waste, which has a calorific value of at least say 6.3 million joules, megajoules or more, this can be utilized for generating energy. So this has a potential for converting into energy through thermochemical routes. So it can be directly used as a fuel or can be converted into RDF by suitable pretreatment technique. I hope you are aware of RDF, refuse derived fuel. So the combustible fraction can be pretreated to further reduce the moisture content or shred it into smaller size, compact it so that the energy density can be improved. So that is how we produce RDF. So the non-recyclable waste can be used for heating purpose or thermal conversion purpose, or can be converted to RDF and then used in the thermal power plants or some other boiler industries. So any other waste with high calorific value can be used in co-processing. So if you see the current practice in cement kilns or thermal power plants, they are mostly depending on the coal reserves, fossil fuels. So we can think of co-processing or co-firing with this refuse derived fuel in thermal power plants so that the dependency on fossil fuel can be reduced. So if you want to set up a thermal waste to energy plant, because now we have the mindset, yes, we have ample scope of converting waste to energy. So can we go for setting up a waste to energy plant? Yes, we can. But if the capacity is 10 ton per day or more, we have to get the approval from SPCB, State Pollution Control Board, as per the environmental clearance. And other than the heating value of the waste or RDF, the criteria met for thermal conversion technique is its low moisture content. The moisture content should be at least less than 45%, but even after that we go for pre-treatment or pre-drying so that the moisture content can be reduced to less than 10% to use it as an RDF. Okay. And the next is fixed carbon content. Fixed carbon content should be 15% or less, and volatile matter should be more, because this is the volatile matter which is being converted to fixed carbon during the conversion process. So volatile matter content should be more, and as mentioned earlier, the heating value should be more than 6.3 million joule per kg, megajoule per kg. So if any recyclable factor, fraction of waste is meeting these criteria, you can think of waste to energy conversion. And if the capacity is more than 10 ton per day, get prior approval for setting up the waste to energy plant. So I'm just reiterating the same thing. What is the need of MSW waste management, and waste management by generating energy out of it, the increasing population, increase in waste generation, and reduced balance in the waste management sector is one aspect. And industrialization and energy demand in par with the depleting fossil fuel reserve demands more energy reserve or energy sources. So let us put these two together to make our waste to energy conversion as a demanding area. And this waste to energy conversion can address the imbalance in waste management as well as the depleting reserve, so that the waste is managed properly and the energy demand is met by the energy created out of the waste to energy process. So just addressing two major SDGs, so we can say affordable energy and clean energy from the waste converted through different process to the energy. So it can be a thermal energy or the solid liquid biofuel or biochar that is produced from the waste to energy conversion process. And of course, it can give the sustainable cities and communities, clean cities. So this is directly catered to these two sustainable development goals, and indirectly it is meeting many other SDGs, say for example, health and hygiene, right? So all this is met if you go for waste to energy conversion techniques. Now, where can we use the RDF or even the agro residues directly, right? So if you are thinking of again waste to energy plant, who will be the buyer for the converted product of your waste to energy facility? So if you have the segregated, say, combustible fraction from MSW, if you have that SCF, segregated combustible fraction, or even many of the agro residues have the calorific value more than 6.3 megajoule per kg. So in par with our SWM rule, this can be used as a fuel in boiler or thermal power plants. Or if you want to give energy densification, we can go for converting this into RDF, as I mentioned previously, by removing the moisture, shredding and size reduction. Pelletization or compaction can be done to do energy densification. And if you are doing energy densification, we are getting the high energy content, which is in par with the conventional fuel that is used in thermal power plants or cement kilns. So we can go for the intended application, like it can be used in boilers for heating if the energy density is comparatively less. The densification can cater its use in, say, cement kilns or in thermal power plants, either as a sole source or co-processing with the existing biofuel like coal. And if you do so, the intended aim is to substitute the current fossil fuel reserve by the agro residues or combustible fraction by at least 6%. So we are aiming at least 6% reduction in the fuel intake in boilers by replacing it with the agricultural residues, or at least 10% fuel intake in the coming 2 years. Coming 2 years from the implementation of the latest amendment, that is October 2015. 3 years, 10% reduction in fuel, commercial, conventional fuel intake in the 3 years, or by RDF grade 2 and 3. So it's comparatively lesser in quality, but even with this, we can aim at least 15% reduction in the fuel intake of the thermal power plant or cement kiln in the coming 6 years. Yes. So we have different techniques for waste to energy conversion, and the biochemical process, which we will not be covering much into this because we are more focusing on the thermochemical conversion techniques. But of course, we can go for biochemical process for converting your waste to energy if you have the biodegradable fraction of solid waste. And as we know earlier, around 50% of the MSW is biodegradable. So it can be converted through fermentation or anaerobic digestion to the respective value added products. But biological process, the slow process, of course, the operating condition or cost may be less in terms of the reactor operation. But if you see the land requirement for the biological degradation process, because of its slow degradation rate, the high cost is involved most of the time in biodegradation process. And of course, microbes are susceptible to the environmental variations. So we can expect the dependency of operating conditions or environmental conditions on the end product generation. Now coming to thermochemical process, so we have incineration, burning of biomass, right? Burning of waste which has comparatively high heating value and as far as possible low sulfur or other pollutants, because if you see most of the incinerators, if you don't do proper pre-treatment, or if you won't install the air pollution control devices, it can generate furan and dioxin, and direct release into the environment is harmful. Gasification, yes, this will also give you the volume reduction. This is again burning in partial oxygen atmosphere depending on the intended end products. Here again the reactor choking and char formation, again based on the type of the feedstock, the choking can be an issue. Pyrolysis, yes, it also has its pros and cons, right? Low heating rate if you are going for conventional pyrolysis, more starting time from one set of reactor to the other, high power requirement, because in pyrolysis we are increasing the temperature to 500, 600 or even more during the treatment time. Low quality product, because we are aiming for 3 different streams of product: bio oil, biochar and gas, right, during the pyrolysis. But how much is the relative portion of this? Quality of individual streams of pyrolysis byproduct, that again is a question if you are going for conventional pyrolysis process. So it is left to the wisdom of waste to energy operator to go for a suitable technique catering to the type of waste and the operating conditions that you can maintain. So if you see the existing commercial waste to energy plant, we have many incinerators, which is taking the combustible fraction of waste. And coming to the biological biodegradation or the biodegradable fraction of solid waste, anaerobic digester is common, or I can add even composting to it. Right? The 2 major streams to cater: the non-biodegradable waste and biodegradable waste. But if you see this waste to energy techniques, especially if you go for incinerator, it is not carbon neutral, because we are depending mainly on the electricity. We need to go for auxiliary fuel for still burning of waste, especially for removing the moisture content and so on. And if you see the anaerobic digester, the slow process, or it may require large area. And most of the waste to energy technique which is in place at present is centralized facility. So what is the drawback with centralized facility? Continuous supply, air pollution. So if you have a decentralized or centralized technique, transportation, right? So involve high storage and transportation cost, because if you see the nearest facility from this campus to the campus is the source of waste generation, IIT Bhubaneswar, and if I want to transport the waste generated to Bhubaneswar city, so you can think of the transportation cost, the pollution involved during the transport, right? And of course, for transport, we are again depending on fossil fuel, right? So this involves high transportation cost, storage cost, and the centralized facility. Sometimes the waste coming to the facility is not uniform and not non-timely arrival. That can also affect the waste to energy plant. And if you see this particular, especially if you are going for the biological degradation technique, waste segregation, mostly for all the techniques, the waste segregation is required, because if you go for food waste incineration, not practical or it's not economic. And if you go for plastic to anaerobic digestion, it is not possible. Rather, plastic in the anaerobic digester will reduce the efficiency of conversion of biodegradable waste into radioactive. So what can we do? We always have mixed waste. Segregation is the major issue, and we are trying to make different ways of segregating waste, again emphasizing the solid waste management rule, the waste segregation from the source. So this is a typical case study of material recovery facility in Bhubaneswar, Bhubaneswar city again emphasized the waste segregation from source. The wet waste and dry waste is separately collected, and the waste that is arriving from this MRF facility is further segregated, because even if you go for wet dry segregation process, the wet waste is collected in plastic bag, right? The food waste is collected in the LDP, the garbage bag, which is plastic. So again, we need to go for one segregation at the facility, and let me think of the segregation at the facility and biodegradable fraction, which is going to AD or compost, anaerobic digester or composting process to get me the humus or compost, and the rest of combustible fraction or non-biodegradable fraction is compressed, densified, and is used as RDF, refuse derived fuel, and this finds its way to the nearest cement kiln in Bhubaneswar city. But if you see the economics of operating this waste management facility at Bhubaneswar, the expenditure per month, which include the salary of the manpower, human resource, consumables, electricity cost, vehicle for collection of waste from different corners of the city to this MRF facility, totaling to around 18 lakhs per month in one composting facility or in one MRF facility in Bhubaneswar. We have many such facilities in the city. And coming to the revenue generation. If you see the revenue generation, of course, we can get revenue from the RDF and revenue from the compost. But we see the value of the revenue generated from this, and of course the user charge, right? They have to charge for the waste collection. So including all this, summing up all this, the income is around 1/3 of the expenditure. So we are, by doing this facility, we are only going for waste management, but it is not coming waste to well, right? If you see the net profit from this facility. So there is always a need of advanced techniques. There is no single solution to cater all this, but let us move on and search for a facility which can take mixed waste, convert it into value added products, and the same process or technology we can deliver variety of products based on the feedstock that is coming to that facility, and of course everything we need in quicker manner, rapid conversion with good quality end product, easily controllable operating parameters, and of course profitable, right? At the end we need money. So just we are looking in whether microwave assisted pyrolysis can address few, many, or all of this requirement for our waste to energy facility. What is microwave? All are familiar with microwave oven, but where the microwave lies in the electromagnetic spectrum? If you see the position of microwave in the electromagnetic spectrum, it is of high wavelength, 1 millimeter to say 1 meter. The energy of microwave as such is very less. You may be familiar with using UV, ultraviolet rays, because its energy is high, so it can disrupt the chemical bonds, right? And even pollutant remediation can be done with UV. But how microwave, a comparatively lower energy region, but the microwave has some specific heating potential. It has the heating mechanism of dipolar polarization. This is how the dipole will get reoriented in the microwave to get the medium heated. And the other one is conduction mechanism. So conduction mechanism is by the electrons, the free electrons that can move in the medium on irradiation of microwave. And if I say interfacial polarization, it is a mix of the dipole orientation and conduction mechanism. So we can expect, like say pure water, mineral water and tap water. If we keep in microwave, which one you expect will be heated up? Or I say demineralized water, no minerals, and the other side I have tap water with lot of minerals or pollutants. Tap water, here the mechanism is conduction mechanism, and if you have some dipoles, the dipolar orientation, that can also help in heating up the pollutants. So if you see the commercial, the frequency of microwave is 300 megahertz to 300 gigahertz, 1 millimeter to 1 meter wavelength, but for commercial application we go for 2.45 gigahertz. This is the same frequency of the domestic microwave oven. And this microwave, due to the specific heating mechanism, it gives you volumetric heating. Starts from the atomic level towards the periphery, and more efficient heating or rapid heating, giving the high product heat. So if you see the temperature profile inside the microwave or reactor, or in a conventional heating process. So in a conventional heating process, it is heating by conduction mechanism. So the periphery is heated first and then going to the interiors. It is just reverse what is happening in the microwave reactor, inside out, not the movie, but it starts from the atomic level and then going towards the periphery. But whether all materials will be heated up with microwave? No. So can I use all the type of waste to be converted by microwave assisted pyrolysis? No. If not, again the segregation will be an issue, right? So how can I segregate the collected waste based on which can be heated by microwave, which cannot be heated by microwave? Should I go for that? See, we are going for a technique which can avoid segregation of waste. And now if you tell me I have to segregate the waste based on which will be heated up or not heated up by microwave, I cannot address the issue. For example, I can say food waste, right? Biomass will be heated up by microwave because it has carbon content. Carbon is a good absorber of microwave. Even you can expect a temperature of more than 1000 degrees Celsius with a carbon containing material in microwave. It has a specific phenomena called hotspot formation. But if you take plastic, it will not be heated up by microwave. Because you can see you are baking pizza in microwave oven, right? Your container is not heated up, but the pizza is baked. So what should I do with a mixed waste which has some part which can be heated up by microwave and the other not? And what makes this differentiation of microwave heating? It mainly depends on the dielectric property of the material. So I can make a material which cannot be heated up in microwave to be converted by microwave assisted process, provided I will use a microwave absorber or susceptor. So here is the role of microwave absorber or susceptor. If a non-microwave absorbing material have to be heated up in a microwave oven, we can think of a susceptor. Now what is susceptor? It has a good dielectric property. So here let me take you through the dielectric constant. So what is dielectric constant? It is the ability of a particle or a material to absorb electromagnetic radiation. So the electromagnetic radiation what we are talking here is about microwave, right? And the dielectric loss factor is the amount of the absorbed electromagnetic radiation that is converted to heat. Now I have a term here, loss tangent. So loss tangent is high. What does that mean? The equation for loss tangent, you can see epsilon naught by epsilon. So what if the loss tangent is high? Conversion is high. So amount of absorbed electromagnetic radiation, mostly it is converted to heat. So if I have a material with good loss tangent, we can expect increased temperature profile inside the microwave. So these are different properties of microwave. It should have good dielectric property, that means it should absorb microwave. It should have high loss tangent, that means the absorbed microwave should be converted to thermal energy. And the thermal energy should be dissipated easily to biomass or the waste that you are converting in the process. And while doing all this, it should be thermally stable as well. Right? So we should think of a microwave absorber or susceptor inside your reactor which can cater this. So we have tried several such materials, cement, fly ash, activated carbon. Carbon is always microwave absorber. Water we will not add into waste, but I want to say that water content in the mixed waste can also act as an absorber in your microwave pyrolysis process. And silicon carbide, now we are using zirconium alloy which has even more high tangent, low tangent than the silicon carbide to increase the heating profile. Yes, so we can use microwave for waste to energy conversion, even if the material cannot be heated up by microwave, by using suitable absorber or susceptor, and again by setting the temperature. So here I am not going into any pressure based technologies. So hydrothermal liquefaction, hydrothermal carbonization is a pressure based technology, but here just by playing with the temperature we can convert the microwave assisted technique into torrefaction, pyrolysis or gasification. So mainly it lies in the range of temperature that we use, and we can fix the power range of microwave so that the temperature can be retained within the required limit. For example, if I go for comparatively lower temperature, say 200 to 350 degrees Celsius, we can think of using a lower microwave power and longer residence time, so that the volatilization will not happen, rather it is carbonization to give you biochar. So you will yield more solid residue if you go for torrefaction. Pyrolysis, again we have three variants: flash, fast or slow pyrolysis. All this differentiation is because of its heating rate. Heating rate again because of the microwave power that you select. So you can differentiate into these three, and the three variant, again slow pyrolysis will yield more biochar, fast pyrolysis to bio oil, and flash pyrolysis is in par with the gasification to yield more gaseous residue. Now if you want to tune your microwave assisted technique for waste conversion, map yield of the product, it depends on feedstock. So you cannot expect, say, biomass to give you high quality bio oil or plastic to give you high quality biochar. It's not possible. So first you see the limitations of your feedstock. So you have to tune whether you are focusing on your feedstock conversion or you are starting from tail end to select the feedstock. For example, if your aim is to produce more bio oil, you can go in search of a suitable feedstock, tail to head. Or if you have this much crop residue to be processed by microwave pyrolysis, then you see which of the end product will be suitable. Okay? So that way you can think of the feedstock characterization by its chemical, physical or size parameter. I will not go much detail into this because chemical is our CHNS analysis. Physical, that is moisture content, volatile matter content, ash content, so on and so forth. Okay. And coming to the reactor, of course, the microwave reactor design. The design of reactor, say if you have spherical, longitudinal, horizontal flow, vertical flow, that is one aspect, or even the operation mode. Batch, semi-batch, continuous reactor can be possible. And microwave cavity is more or less the design parameter of microwave. So it is the resonator which generates the microwave. Again, that is something like magnetron. Right? So the magnetron specification also give the microwave yield. It also depends on the microwave yield. Now coming to the process parameters, yes, here we can play some role because little to do with the feedstock, and so is the reactor fabrication. So in the operating condition, you can think of setting the microwave power. Heating rate can be controlled by using suitable susceptor or microwave power, and what temperature you want to do the conversion process, quantity of feedstock taken per batch, which susceptor you are using, or you are going for an additional catalyst or reaction time. All these can play some role. And of course, again, the end products. I will not spend much time here because this was the point of discussion in the last session as well. The biochar can be used for soil quality improvement, or it can be modified to use it for water wastewater treatment, and it can again be used for electrochemical methods because it can be used as an electrode, good conductor, and of course as a fuel. And coming to bio oil, again it can be used in chemical pure synthetic chemical production, or can used as fuel for petrochemical industries or power generation. So keeping this, we are doing different microwave assisted pyrolysis for variety of feedstock. So we started the microwave based study, I should say around from 2007 or so, and now we have done the conversion of different variety of feedstock, starting with food waste, crop residue, forest residue, polyculture, microalgae. So here we have isolated microalgae from nearby pond. It is a mixed culture, and then it is grown in wastewater. So it's specifically grey water. So grey water was the medium for microalgae. Wastewater, grey water was treated, microalgal growth happened, and the microalgae was then converted to biofuel. So it's gone through a stepwise acclimatization process and so on. And of course, different types of plastic waste, end of life membrane. So membrane based water treatment, the end of life membrane, the discarding is a major problem. So we have again sort of converting this into biofuels, or even packaging waste. The cardboard or multi-layer packaging can also be converted to biofuel. But today I will just go through few results that we got from the commingled food waste. Why mixed food waste? Because we are emphasizing on segregation. As I mentioned, we have lot of food waste generated, starting with the non-eaten, or even the different supply chain of food waste production, starting from the crop production, processing, then the food processing and so on. So a lot of food waste is generated, and plastic as such, if we tell this as plastic waste, which is no longer in use, because we have to reuse as far as possible, and once it is discarded, we call it as plastic waste. So most of the time we get food waste and plastic waste together in dustbin, right? So if you want to take this to a biological treatment process, the bare minimum thing you need to do is the separation of the garbage bag from the food waste. So we just thought of, instead of disposal, dumping, landfilling with its own pros and cons, why can we convert this mix? As such, we collect from the garbage bin into MAP reactor for converting it into end products. So I'll just present few of these results from the study of converting the mixed waste through MAP into bio oil and biochar. As we know, food waste is not a uniform in nature. The waste you get today in the dustbin is not the same as tomorrow. So we just thought of collecting an average food waste composition. And you can see there is lot of variation. For example, if you see the moisture content, 63 plus or minus 10. Right? So you can think of variation in the initial properties of food waste. But what is interesting here is it has high volatile matter. So when you have a waste with high volatile matter, we can think of thermochemical conversion. And if you see the carbon, again, ash content is very less. Another good point to be taken for thermochemical conversion: low ash content, high volatile matter content. And if you see the LDPE, of course, it has very low moisture content, high volatile matter content, so it can be converted through thermochemical process, good carbon content. Right? It is apt for thermochemical conversion process, but if you see as such, as generated food waste and LDPE has comparatively low heating value, it is not meeting our RDF criteria, right? Now, if you want to go for thermochemical conversion technique, I think this question has pondered in the last session also. what can be the first step to understand your waste for its thermochemical conversion potential? To me, it is the TGA. We can perform the thermogravimetric analysis and see the degradation profile of your feedstock with respect to temperature. So here you can see the TG of food waste and LDPE. So the first portion, the moisture content removal. In case of food waste, so you can see within 100 to 120 degrees Celsius, the moisture is removed and the volatile matter degradation starts. But if I do a pyrolysis of food waste and plastic at say 200 degrees Celsius, I can expect some degradation of food waste, but the plastic is still intact because the plastic degradation starts at a temperature say more than 300 to 400. So in a mixed waste, you can perform the TGA of the mixed waste so that you can see the degradation profile and the temperature at which you can set your reactor for the thermal degradation process. So this is a schematic of our reactor, as the pyrolysis has to be done in oxygen-free atmosphere. Initial process need to be the nitrogen filling, nitrogen purging. You can even think of argon or vacuum pyrolysis. The aim is to remove oxygen from this atmosphere. And once the inert condition is emphasized, you can think of switching on the microwave, the reactor, so that the heating takes place. And here again we are using different susceptors to enhance the microwave heating. And now with respect to time, we can expect the conversion of the biomass or feedstock into the biochar as well as the condensable fraction of bio oil. So this can be condensed and collected in the biofuel tank. And most of our study again focus on the biochar and bio oil fraction, and we ensure that the rest of the biogas goes through the absorption column so that there is no environmental pollution that happens from the pie gas. So this is the lab scale reactor with the schematic. Now different end products of food waste, LDPE pyrolysis. You can see again based on the initial quality of feedstock, food waste bio oil. I should not say this is bio oil, this is mostly water. Food waste and plastic, so 5% plastic, you can see the density of bio oil is comparatively improved. Increase in LDPE content is giving you the light fraction and heavy hydrocarbon, and so is the change in the solid residue biochar component. So based on the feedstock, you can expect a variation in the end product even if you keep the reaction conditions same. So this is another example, like say if plastic cannot be heated up, we are using an absorber. So in this case, you can see the heating profile of food waste alone or plastic alone. So again, this is within 1200 degrees Celsius, sorry, seconds, rapid heating, right? But if you are using the GAC, again you can see within 600 seconds, there is a sharp rise in temperature, and the credit goes to GAC, the microwave susceptor. Okay, so you can use suitable susceptor for increasing the heating rate. Now coming to the optimization, process optimization, we can think of optimizing the operating parameters. So here we have tried with the temperature, percentage of LDPE in the feedstock, and the residence time to get the maximum bio oil yield with minimum total acid number, tan. Higher the tan, more will be the corrosivity of bio oil. So we have to reduce tan and increase bio oil. So this is the 3D response plot, because each operating parameters can affect your end product yield and quality. So this is the interactive effect. So if you see the first image, the interactive effect of the percentage of LDPE and the temperature of treatment. So you can the maximum around 42% of bio oil yield was obtained at this particular optimum range. So is the interactive effect of residence time and LDPE in feedstock. And at the end, this is the equation generated from ANOVA to predict the bio oil yield for a given percentage of LDP, treatment time as well as the temperature. The same thing we have done for the bio-oil quality, that is total acid number. So what is the interactive effect of each of these operating parameters, that is LDP and residence time, or residence time and LDP, temperature and LDP, or temperature and residence time in the total acid number of generated bio-oil, and this is the equation for prediction. And we could see that the several reaction mechanism was involved here. For example, your food waste has cellulose, starch or heavy cellulose. LDP is a long chain hydrocarbon. The mechanism may be direct thermal breakdown from the microwave pyrolysis, or by the microwave interaction. Thermal breakdown of the parent compound is one mechanism, and you can even think of the secondary cracking of the large chain hydrocarbons to yield you subsequent byproducts. So if you extend the time, so this is again by cracking or thermal degradation, we got different products. While extending the time, we can expect again the further cracking of the generated product in the first stage to yield you more and more end product by cessation of the long chain hydrocarbon. But at times, as we have seen earlier, the bio-oil from food waste is mostly moisture, and even with 5% LDP content, the quality of bio-oil is not that good. So we can think of upgradation of bio-oil. So this is what we have done for upgrading bio-oil to biodiesel or biofuel standard. The bio-oil is taken through a hydrodeoxygenation process, HDO process. The main aim here is to remove the oxygen containing functional group or the oxygen as such from the bio-oil, so that the heating value can be improved. So we are adding hydrogen at high pressure, high temperature condition in presence of catalyst, so that oxygen is expelled out from your bio-oil to improve the quality. And different reaction mechanisms involved: hydrogenolysis, hydrogenation, dealkalization, dehydration, so on and so forth. So this is the HDO reactor setup. So in this HDO reactor setup, you can see the bio-oil is mixed with butanol. Butanol is used to reduce the tar formation or increase the fluidity of your bio-oil. And then this is taken through the column of alumina bed for easily flowing, making the bio-oil flow smoothly through the catalyst. And catalyst, again, we have prepared our own catalyst, which is supported on zirconia, and this is housed inside the alumina beads. You can see the entire column of alumina beads with the catalyst, which was supported on the zirconia bead. And this was regulated by temperature and pressure. So we checked what is the effect of different temperature and pressure for the quality of upgraded bio-oil. So this is the actual reactor setup with different components taken separately. So the gas cylinder, so this is the inside of the reactor column where the catalyst is placed, pressure control panel, and this is the inline GCMS, so that the end product quality can be assessed. Now we can see the HDO bio-oil versus the bio-oil that we obtained from MAP. So the first figure here, it says, so we can see the lipid region, sugar, pyrolytic lignin region and protein region marked in different color. So here is the lipid, and pink color shows the sugar derivatives and so on. The left side is the wax. If you can recall our figure, we had a light and heavy fraction of bio-oil when we had 13% LDPE. Now this is the Van Craven diagram of the wax fraction, and the other one is the lighter fraction of bio-oil. When you take it to different treatment time, temperature, say for example 48 hours and 200 degrees Celsius for the heavy fraction, and say 48 hours and 200 degrees Celsius for the light fraction of bio-oil, and then say 24 hours 300 degrees Celsius for the heavy fraction, so on and so forth. You can see the relative compounds present in the lignin region sugar derivative is varying. That means we can play with the temperature and pressure or treatment time in the HDO reactor to yield the required quality of end product. So this is the end product quality comparison with the bio oil and biodiesel standard. So if you see the bio oil obtained from MAP, again the mixed food waste LDP through MAP generated a bio oil with a density of say around 1.1, and HDO bio oil the density is slightly reduced. pH was 4.9, that means tan value is high. pH acidic means corrosivity of the bio oil. So we could improve the pH to 6.3, which is giving us the standard in par with the biodiesel. And the moisture content in the bio oil 35%, but it is reduced to 4.1, so 4%, and the heating value is also improved. Total acid pH is given here at TAN. I will compare in the second. So it is coming around 40 also. Yeah. Now 48 hours. So it again depends on which quality product you need. So if you need pure sugar derivative, or if you want to only improve the heating value, moisture content reduction is the major role. Right, so in that case we can go for even 7 hours could be giving a higher heating value. But taking a synthetic pure chemical from this bio oil, then you can think of. So I just want to mention here that you can play with time, temperature and pressure, but pressure here we have used 70 bars in all the cases, but we can play with even pressure to change the relative composition of end product. Now coming to stability, because most of the time we need storage value for the end product. So the stability, again you can see the stability of HDO bio oil is significantly improved. For example, we can get the density is more or less the same, stable, and so is pH. So here we have the pH with respect to time for the HDO bio oil, but you can see the variation in pH for the bio oil before the hydrodeoxynation process, and the moisture content of HDO bio oil is always constant, but not the case in case of the bio oil and so on. So it means the quality is retained even after 60 days of storage, or I can say the stability is improved by deoxygenation process. Now this is the biochar. So the main focus of the study was on bio oil production, but again as I mentioned earlier, we cannot expect only biochar or only bio oil from this. Only what we can do is maximizing one particular end product. And here we are dealing with food waste, so I cannot expect 70% of bio oil coming from food waste. So what we could get was around 40% bio oil and 40% biochar. So now what to do with this biochar? So we have again done the quality analysis with this biochar. Again food waste LDP biochar, and checked with the RDF quality of EU as well as Indian standards. So I'm just emphasizing few of this. The moisture content is very less, ash content too low, good quality RDF, and we have high fixed carbon content and improved heating value, which is much higher than the required standard of RDF. So this is just to say the role of different susceptors. As we mentioned earlier, we can use GAC as susceptor, any carbon material for that sake. So if you are not aware of which susceptor to be used, you can just think of carbon, the best friend of microwave. So here we have used GAC at the first stage, and you can see with GAC the heating profile with increasing the GAC, and then in the first run we have used GAC, and the first run of MAP is giving you biochar and bio oil. What to do in the second run? Again I will add GAC. Yes, biochar is again carbonaceous. So we thought of recirculating or reusing the biochar from the first cycle to be used as a microwave susceptor in the second cycle. But biochar is again giving you, this biochar improvement in the percentage in biochar is increasing the heating rate. So you can rely on your susceptor in the first run of your microwave pyrolysis and try to use the biochar in the subsequent run as susceptor. So this is giving a good heating profile and a better quality biochar as well. So this is the TGA profile of the biochar obtained from different runs. So it's a stable biochar by recirculating. And if you see here the end products, so with 3% biochar recirculation, it's almost 50-50 for biochar and bio-oil, 44% and 46% bio-oil and biochar. If I increase the recirculating percentage of biochar, more and more volatile is formed, and you can see up to 7% it is giving me 52% bio-oil. So more the percentage of biochar in the recirculation, more is the bio-oil formation up to 7%. So what happens next? When it is 10%, yes, the 40%, 52% bio-oil which I could get with 7% biochar recirculation got secondary cracking and the 5-gas generation is improved. So you can again optimize your recirculation. So if you are focusing on more solid product, think of having comparatively lower biochar recirculation, and if you improve it, I can think of secondary cracking, volatile formation, and bio-oil or syngas formation. So this is again the property of the different biochar. So I'm not going into detail of this. So I'll just mention that each of this biochar using different recirculation ratio of biochar in the subsequent run was giving very high yield heating value of biochar, much more than even RDF grade 1. Yes, we are always ensuring the uniform distribution in the feedstock. So this is just the morphological analysis. If you want to use the biochar for say water treatment purpose or so, then we have to think of the porosity, and we have also done the FTIR analysis, surface area analysis, to see what is the functional group, surface area, so on and so forth, to use it for the water treatment purpose. So here you can see the 7% biochar was giving a best porous structure compared to the other. So again, if your aim is to use the biochar as a water treatment method, say absorber or catalyst, you can tune your treatment process accordingly. The biochar as such is stable. So if you use it for second time, you are still retaining the same biochar, right? So we could get the improvements. Same biochar can be reused again and again. But the thing is, from the second round, we are getting a new set of biochar, right? So again, take a fraction of this and recirculate. That I think that may be for a catalyst. So I have mentioned here. So if you are using it as a catalyst for wastewater treatment, so initially you have a biochar, it will have some surface properties, surface functional group, porous structure, right? If you are using it for water treatment, it can happen that your pores will be clogged with pollutants. So maximum 1-2 times you can recirculate if it is an adsorption process. Otherwise, you have to regenerate the biochar for subsequent use. But when you are using it as a susceptor in the microwave reactor, you don't need to bother segregating. Whatever biochar you get in the second run, you just recirculate a fixed percentage of that into the subsequent run. My question is, how can you continuously heat the same biochar? Because the first set you have biochar produced, right? A part of this you are recirculating with the new feedstock. So you got a new set of biochar. Now from that you can take a few percentage of it, recirculate it with another set of feedstock. So new biochar is obtained. Because you cannot think of same biochar in MAP process. It is mixed with a new set of feedstock to give you a new biochar. So this is again the effect of different susceptors. So we can, those who are doing research in this, you can even think of trying with different susceptor or developing your own susceptor to improve the quality yield. So here just a comparison with different susceptors, GAC, silica gel, cement and fly ash. The temperature or heating profile is here, and the stability of biochar with temperature, the TGA profile is seen, and you can see the relative end product yield. So this is only in present in terms of the end product yield, the percentage variation, and I can say with different susceptor even the quality of end product is varying. So we can do a research on which susceptor is suitable for obtaining a particular yield and particular quality of end product. Lot of scope for research in that area as well. So again the comparison of I'm just comparing with the feedstock, stability of feedstock, the temperature, thermal degradation profile with different biochar produced using different susceptors. Just to ensure that volatile matter is carbonized. Again, using different susceptors for the same feedstock, food waste and LDPE, the heating value is improved much better than the RDF. You may have, so this is if you want to use it for a catalyst or water treatment purpose, again think of surface characterization and so on. Now coming to the right end of the slide, you can see toxicity analysis, because there may be a question for safe disposal of biochar, or if you are using it as a safe fertilizer in soil. So how about the leaching of heavy metals and polluting the land or surface water? This we have done the toxicity analysis of biochar produced through different susceptors with the same feedstock, food waste and LDPE, and you can see that the microbial inhibition is very less, or I can say microbes could grow successfully in each of these biochar, and it is safe for disposal. And we have also tested the pi gas, the gas that is coming out of it. It is mostly methane or H2. So if you want to again tune your process, you can think of green hydrogen generation from this technique. So this is again the bio oil property compared with different standards, and as I mentioned, with different susceptor, with the different recirculation ratios, the quality of end product varies. The bio oil quality you can see with different percentage of granular activated carbon or 3 to 10% biochar recirculation, the pH, density, moisture content and so on. And so is the individual chemical composition in bio oil. So as far as our research is concerned, we are not looking into individual component fraction, but overall what is the pH, tan value or heating value. So those who are doing in research of synthesizing pure chemicals, they can focus on more detailed analysis of chemical composition as well. So as I mentioned, we were doing with the microwave pyrolysis with different feedstock. To list few, this is just the yield from different products. The food waste LDP, food waste plus LDP, this is what we are talking so far. And we have hemp herd, crop residue, microalgae, rice straw, COVID waste, and we have many more to say. So I just say like different microwave assisted map parameters. So it was not uniform. So we have optimized it for different feedstock for different conditions, and we can see the yield also varies with respect to field stock. So in a nutshell, this is what we are doing in the MAP process for waste to energy conversion. Take any waste for that matter, check its initial characteristics, do the TGA profile and see which temperature is suitable for its conversion. You can directly convert that into biochar or pelletize it to convert into biochar pellets. So those who are doing for pelletization, pelletized fuel formation, I'll suggest you to go for pelletization before microwave pyrolysis process, because it is very difficult to convert your biochar to pellets. You may need to add separate binders. So think of feedstock pelletization, optimize your MAP process and get either biochar or biochar pellets, and the bio oil can be the other end product. Based on your need, optimize the bio oil production or biochar production subject to the restriction of the feedstock characteristics. So here the uniform heating, the credit goes to the carbon content in your feedstock. Because biomass, again, it has high carbon content, so we can expect the uniform heating. Even with pellets, we could get the uniform heating of the biomass. It is not a single time, so we can say that different times were used. So 15 to 20 minutes was the maximum time we have used for all this MAP process, not beyond. So I hope now you will agree with MAP has some role in waste to energy technique. So let us think of the waste that is coming from, say, agricultural residue, or even the residential or commercial sound like food waste or plastic, or the waste from some industrial process. Let us take it through the MAP process, microwave assisted pyrolysis. Optimize your process for biochar production, oil production, or the syngas production based on your aim, and then utilize it for subsequent process. So for example, biochar, you can use it again for industrial application as fuel, or this can be used in agriculture. It can be used as a slow release fertilizer in agriculture, or it can improve the water holding capacity of soil. So it has its way in agriculture as well. And coming to bio oil, as such, from some feedstock, the bio oil as such can be used as a fuel, or think of upgradation to use it as a fuel in transportation vehicles, and of course the biogas as for power generation. I hope we'll stop here, and this is the video of, now we have a pilot scale reactor of microwave pyrolysis, which is completely working in solar power. So this has again that shredder mounted on the surface, which can shred your feedstock into required size, and we are converting anything and everything that we get for that matter, and trying to optimize the pyrolysis condition to convert this into value added end products. So these are few feedstock: plastic waste, hemp hurt, packaging waste, and these are some pellets which is then later converted into biochar. So this is the membrane material from end of life arrow membrane. We have used it again to convert this into bio oil. So this will be shredded. Agricultural residue can be shredded in the shredder, and it will go to the pyrolysis reaction unit. We have full process control to set the temperature, reaction time, and there are 30 different steps of setting the temperature and reaction time. So if you need step temperature profile, you can think of having the temperature profile as per requirement. So this is the nitrogen flow regulator to make inert atmosphere inside the reactor. The control panel to set the temperature at different steps. So you can just step temperature profile or step temperature profile as you need, and decide your reaction time and we have 4 set of magnetrons. That means it can operate in 6 kilowatt or 3 kilowatt based on the quantity of feedstock you need to process. And these are different end products obtained from the MAP process. The oil collection unit with 3 condensation unit. So sometimes we can get even 3 different quality of bio oil that is condensed in the subsequent condensation unit. So these are some of the end products. Biochar from sawdust, the pelletized biochar. And various bio-oil fraction from multiple feedstocks. We have calculated the net energy gain in terms of the total energy input. That was done for the lab scale reactor which was operating with electric energy, right? The energy input and the energy output in terms of the heating value and the yield of product. So in most of the time you are getting a net energy gain more than 100%. That means the energy input what we give in terms of calorific value, yes. Yes. The optimum condition it is more. Yes. See that again the microwave can take the water because water is a microwave susceptor, but then the quality of end product may vary, especially if you are going for bio oil. The feedstock with high water content will yield you bio oil with high water content. Right? So you can think of pre-drying and have again used sun drying to reduce the electricity consumption. Up to 30% also the water content can be easily taken into microwave reactor, provided your focus is on biochar. We have tried with 1 kg per even 50 gram per batch to 1 kg per batch or so. Now this pilot scale reactor can take 10 kg per hour. So in one batch, again it depends on the density of material, up to 10 kg can be processed in one batch. Yes. So far the maximum time we can say 30 minutes. For none of the feedstock we went beyond. My students are here, they can even ascertain that we are not going for more than 30 minutes for any feedstock. Time taken is the same. So what we are doing is the power input. So we have started with 1 kilowatt microwave reactor in lab scale. Now we have the 6 kilowatt microwave reactor in pilot scale. And this can be even modified to improve 9 to 12 kilowatt. So based on your feedstock, the magnetron capacity can be improved, but the reaction time is same. Within 30 minutes, and it is not advisable to go beyond that. So it's better. Yes, conventional pyrolysis 4 to 6 hours is the reaction time. The same or better quality biochar we could get here in 30 minutes. Shredding, this has an inline shredder to shred it and feed it into the microwave reactor. So if you need a shredded biochar. So if you are going for pelletization, we are using a separate pelletization unit, converting it into pellets and then feed into the pyrolyzer. So that you will get the biochar pellets. So this is something like the coal. Size of coal we are making the. Yes, yes, we are doing it with rice husk, rice straw, even other crop residues, wood chips. It is applicable for this. Hmm. Mhm. Yes, so what we are doing is first TGA will give you the characteristics of feedstock, at which temperature it will start degrading or volatilizing. Once you know the temperature, the next is in the MAP reactor you can play with the heating rate. So heating rate so that the reaction time can be reduced. Now how to improve the heating rate? You can think of suitable susceptor with high low tangent. 100%? 100% heating of the material, uniform heating of the material. Of course, there may be some reaction error, 5 to 10%, but mostly we are getting the uniform quality of biochar. And I have not looked into the other aspects. Even we can make the nanocellulose carbon dots from different feedstock using microwave pyrolysis. Yes, yes. Nanocellulose or CNT can also be, we are also doing that part. Quantum dots, we could make carbon quantum dots, nanomaterial. But this is only, I have focused more on the biofuel aspects. Yield of biochar. See, the percentage reduction we have done with the rice husk or even rice straw, shredded rice straw, and say the rice straw pellets. The biochar yield is more or less the same. So if we could get maximum 70%, if I remember, 70% yield of biochar from rice husk, rice straw, and so is from the rice straw pellets. Moisture content will obviously leave your feedstock. So if you are saying the other than that, how intense is your carbonization? So carbonization, if you go for the slow pyrolysis or say torrefaction, we can expect that measure of this residue remain in the solid state, so that the volatilization is prevented. So we can think of playing with the heating rate to cater to some extent to the extent of yield of end product. Yes, again I cannot say it is mostly biogas, because say if you go for a rice straw pyrolysis, you cannot expect 50% biogas to be produced. But the thing is, if it was 10 earlier, say if I go for a 300 to 400 degrees Celsius, I may get 10% of biogas. If I go to 800 degrees Celsius also, I may get 30% of biogas. But you cannot tell that yield of biogas will be the maximum. That limitation always comes with the type of feed. Toxicity analysis, so we have done the microbial inhibition study. Like the biochar is fed to the microwave, so we are going with that standard Vibrio fishery test to check whether the microbes can grow in different biochar media. So like we are preparing the leachate from biochar, and that leachate, the microbes are inoculated to the leachate and seeing their growth. So if this leachate is toxic to microwave, the microorganism, the growth will be inhibited. Yes, there is a standard protocol procedure to be followed, the leachate and the inoculation of microorganisms. Yes. Again, leaching process with a different leaching material, not only water. We have tried to extract maximum heavy metal from it and then check it with a microorganism. To ensure that, because biochar, it is carbon sequestration, and we say it is carbon negative technology for microwave pyrolysis, and it will stay long in your soil, and should ensure that the heavy metal leaching will not happen with such a thing. Yes, we have the hydrodeoxynation unit for a lab scale apparatus, a lab scale conversion. $25. Okay. P is the percentage of plastic. T is the time, retention time, treatment time, and T is the temperature. Total acidic number. The volatile, more volatile cracking, and its conversion into bio oil. Okay, thank you.
Hello everyone. For now, we will take a break for 15 minutes, a tea break for 15 minutes, and later we will continue with the next session. So at 11:45, the next session shall start. So I request everyone to be present here by 11:45. Thank you.
Oh, oh,
Okay. Yeah, hello. So, welcome back to the day 4 for the courses. So, this morning, Dr. Rania already uh, explained to you what is the microwave pyrolysis to produce the bio oil. Right now. And after that, it's upgraded into the biodiesel throughout the process. So, these sections, I would like to discuss a little bit more about the sustainable aviation fuels. So, what you understand about sustainable aviation fuels? Now, why we call it a sustainable aviation fuel instead of maybe the biofuel or biojet fuel? So, what is the difference between the sustainable aviation fuel and also the biojet fuel and also the biofuel? What is the main difference? So, yeah, in these courses, I would like to discuss what is the challenges that we are facing when we want to develop the sustainable aviation fuel, and also what is the perspective and also the future for the sustainable aviation fuels. So you see, by looking at the word sustainable fuel, must be overall process, must be sustainable, sustainable. So when we talk about the biofuel, biofuel, yes, is from the organic materials, but sometimes during the production process, it will emitted a lot of the harmful gas, for example, like the CO and also the CO2. So that's why I make it not sustainable. So the word sustainable here is the what? To make sure during the production process also must be green. Must be green. So that's why they use the word sustainable aviation fuel, which is different from the biofuel. Yes, sustainable aviation fuel is one type of the biofuel as well, which is more greener, without emit any emissions during the process as well. Because normally when we use the biofuel, we look at the consumption part, which yes, indeed, the biofuel will emit less emission, harmful emission like the CO2, CO during the combustion, during the consumption. However, during the process, maybe they use a lot of chemicals. So during the process, the energy input is maybe the highest, and also the you emitted the CO and also the CO2. That is the thing. So why sustainable aviation fuel is important? Because the airline already committed to reduce the total net emission to half level by 2050, compared to the 2005. So in order to achieve this one, because it seems like it's impossible, because why? The air transport is increasing year by year, beside the 2 year during the COVID times, but it's increasing. Almost double, triple for every 10 years, double for every 10 years. But how to achieve it to cut into the half by 2025? So they have the phase by phase strategies. First, the ICAO, which is the International Civil Aviation Organization, they already established one benchmark, one policy, which is they call it the COSHA, which is the carbon offsetting and deduction schemes for international aviation. So throughout this, maybe it might be possible. Later I'll tell you more. What about this? This one is the very important steps in order to achieve the direction, which is to reduce the overall emissions from the airline to half or even to net zero, totally net zero throughout this. This one is what? To enable the carbon neutral growth. The carbon neutral growth means to remain. First step, to remain first, as compared to the 2019. not directly to reduce first, to maintain, to compared to 2019. So this is the very initial steps, which most of the, not most of the country, around, I don't know how many country, this mentioned here is 60%. Some of country already committed this policy, which starting from this year, they plan to implement 1%. I think many countries will be planning because they are not enough demand. So that is the perspective of the sustainable aviation fuel. Demand is what? What is the problem? Later on I will tell you. So in demand, so they expect to increase the overall participant country with the large economy like the China, Brazil, and India in 2027. So currently, the sustainable aviation fuel policy, regulation, and also the market mainly are from the European Union country, just European Union country. Even though last few days I mentioned that China also increasing to producing the biojet fuel or sustainable aviation fuel to export into the European country, because they have the demand there. And they have the demand there. Later I will show you with one case study of one of the countries. So how they suffer from this one. Suffer means what? Not because of technology, but they are unable to find a sustainable raw material, sustainable, suitable raw material for the sustainable aviation fuel. That's the thing. So that's why. So during there are two stages. Later on I will show you the graph that they divided into the two stages with the aircraft operation with the emission greater than 10,000 tons of the CO2 need to report their emissions. That is the policy at the very beginning. This one. You see, what is the Corsair doing? Because they are the final aim. The final aim is to achieve half of the total emission is compared to 2005. Correct not? This is the final aim. Then eventually hope to achieve net zero by 2050. But this one, the Corsair have the intermediate plan which they use the benchmarking in 2019 to compare with the 2019 set as a baseline. For the first phase, which is the voluntary stage, which they started in 2021. Hope that over 80% of the growth of the air traffic CO2 after 2000 will be offset. So the pilot phase already done, finished. Now we are moving to the first phase. What I'm discussing here is basically happening in European country, not in Asia. Not in Asia, in European country. This is what happening now. So that's why the Asia will start following. So in these 2 years, we have heard a lot of the term about the sustainable aviation fuel. The same, because it's initially started from the European, which they have their mandatory phase starting from 2007, which they aim to have the last economy country will be join them. So they are exception to give for the some small island or least developed country, because they have one problem we are facing is what is very costly to build the sustainable aviation fuel plant for the certain country or areas. So this is what. So they have their own target, which eventually they will offset by up to 70% of the total emissions. So now that is the background. So that's why make it why the sustainable aviation fuel is important. So now we need to know what is the sustainable aviation fuel. What is that? Is alternative green fuel for the aircraft. So this is to produce by using the renewable feedstock. For example, like the waste oil, the agricultural residues, so that the SAF, the SAF, can be reduced the overall CO2 emission by up to 80% in compared to the using the fossil fuel based fuel. So just now, my question, my initial question, what is the difference between the sustainable aviation fuel? Because the biofuel basically are from the organics and material, correct not? From the plant, animals, and material. However, some of the sources are from the non-biological sources, which make them not sustainable. Then second is, during the production, we will create some harmful emission that I mentioned just now. So they prefer to use the safe, which is the sustainable aviation fuel instead of the biofuel. So make them different. Not only we want to get the green fuel, but the process must be clean, and also the raw material, the feedstock, must be sustainable. So that's why. So normally now the sustainable aviation fuel are from the biomass feedstock with the low carbon content. So the CO2 emission during the combustion can be minimum. So one thing is very important. I also stressed during the last few days. We must design a fuel that's suitable to be used for the engines, not the other way around. After we produce the fuel, then we only design the engine. And not this one is not like the internal combustion engine or generator. The costs to modify the generators and also the internal combustion engine might be relatively low compared to the aircraft. If you want to design the aircraft, can cost easily. I read from the statistic around 1 million for one airplane. Easily 1 million when you want to design or modify something. So that's why. So for the sustainable aviation fuel, we need to design or produce the sustainable aviation fuel that as close possible to the for Jet Air-1 or the fossil aviation fuel. This is a very important thing. Must be designed. So what is the sustainable aviation fuel? No, what is the Jet Air-1 fuel? They are the hydrocarbons. So how we going to turn this all feedstock into just the hydrocarbons. Yeah. So this is the potential pathway. Potential pathway. So commonly, there are few pathway. This one first is the Fischer stroke. So for me, I like to use the second method, which is using the oil directly. One step oil based or the ester based or the fatty acid based resources. So this one is a second method. So there are many methods. So currently throughout this method they already test. So some of the method can blend up to 50%. Can blend up to 50%. That means what? Can blend up to 50%. Still, they can fulfill the ASTM standard. They are certain. I show you or not? I didn't show you the. Yeah, they have the certain ASTM standard they need to follow and or fulfill. So currently, blend up to 50% by using the Fischer hydropress synthesis. Maybe can blend up to 50%. So this is the potential feedstock, biomass feedstock from the wood residue or municipal solid waste. Then this is the process that I like to use, which is also for the hydropress, but my raw materials are from the ester or the oil base or the fatty acid base material, which they come from the used cooking oil, which currently the market is produce the sustainable aviation fuel is from the used cooking oil, because we can get sustainable materials. And animal fat or algae, this one also can blend up to the 50%. So another method is using the micro conversion of the hydrocarbon from the sugar. This one is from the sugar directly. Hydropressing of fermented sugar. So this one can blend up to 10% due to the current regulations. Another method, this one is they synthesize kerosene with the aromatics derived alkane of the light aromatics from what? from the municipal waste or from the forestry residues. Another one, this one is from alcohol directly. This one is much more simple process, but they need to convert it into the alcohol first. Alcohol to the jet. Alcohol to the jet, yes. To alcohol. To jet, yeah, correct. So later on, I will show you for the each pathway, they still have a lot of the step, you see. That is the potential step. So the last one is the catalytics of the hydrothermolysis of the jet fuel, which this one also from the plant oil, soya oil, waste oil, algae oil, and this one the branding also can up to the 50%. 50%. So this is the potential pathway to produce the sustainable aviation fuel. No, all is very, and not to say very complicated. All are the very complicated. Then they have their own challenges and also their own advantage. And also, different pathway they using the different raw materials. Then some of pathway they need to go through a few steps, 1 step, 2 step, 3 step. Some is directly 1 step. Yeah. What? Minimum step can be the single step. Single step you also need to depends on the raw materials. So for me, I use the hydropressing the single step. Later I show you the difference between you see here. Here they use the what 1 step, 2 step, 3 step from the different technique from the different technique different raw material. So nothing wrong and nothing right. Nothing wrong and nothing right. So must be much more easier, because sometimes 3 step is what after you convert you can get more pure sustainable aviation fuel. That's the thing. Much more easy for you to convert, but single step facing the challenges. So maybe the overall year might be relatively low. So how you want to extract out the selectivities? Yep. So then this one in more detail. So this is on more scientific part, which to produce the biojet fuel. Similarly, we have produced from the alcohol to jet, gas to jet, and also the oil to jet and sugar to jet that I show you. This one I recategorize. So for the each process, they have their own method. For example, alcohol to jet. So this is the process, and gas to jet. That is the process, and so on and so forth. Which in our study we are using the oil to gas, which we are using the hydropressing. So for the hydropressing also, you have the 1 step, 2 step, or 3 step. Not necessarily the single step, 1 step, 2 step, and 3 step. You see, for the hydropressing process, these all reaction took place. And these all reaction took place. Then this all reaction will produce what some reaction will produce the CO, some reaction will produce the CO2. So that's why I call my product is just the biojet fuel. I didn't call the sustainable aviation fuel. The biojet fuel, yes, my product is already bioproduct. But during the process, CO2, CO will be produced. That's the thing. So how to make sure, how to minimize the CO during the process, this is what you need to consider. That's the thing. So that to meet the requirement of the sustainable aviation fuel. Not only to meet the property of the jet airline fuel only. That's the thing. To make sure. So of course, for the fuel property, there is the certain STM. If not mistaken, it's 16 something already. They have the standard. If you Google, you can get it easily. What is the standard that you need to fulfill? You see, this one from this process, there are the many other steps, the crackings, and also the separations using the distillations. Then to get your biojet fuel or green diesel or nectar or the light gas because these all will be produced as a byproducts. So some people they produce the green diesel. The green diesel is very close to what? Close to the jet fuel already, biojet fuel, the sustainable fuel. Yeah, just the further step you can upgrade into the jet fuel. The selectivity is almost overlaps. The selectivity is almost overlaps. So yeah, biojet fuel. So this is the potential selectivity. That means the compound what we produce during the biojet fuel. Isoparaffin, paraffin, alkanes, isoalkanes, and the olefin and aromatic compound. So that is the existing markets, and capacity. You see, like what I mentioned. So normally now the market the production run from the what? From the European and US only. So China, I mentioned is starting already. China and Singapore. In Malaysia only the China and Singapore. Yeah, I know. The India also starting already. They announced they want to have a certain policy and build the sustainable aviation plant. Yep. So you see the market. You see the production. The total production capacity is relatively small. You see why I say small? Only 800 kilotons per year only. So relatively small, compared to the demand. Because currently, the overall productions only can accumulate less than 1% of the total needed of the jet fuel. Yeah, less than 1%. Less than 1%. Less than 1%. So there are a lot of the opportunities. This is what I can tell you. A lot of opportunities and a lot of challenges as well. So it's a total renewable. Yeah, you see. Yeah, you see. This one still divided into the two parts. One is the total sustainable fuel. It's the total renewable diesel only. Yeah, renewable diesel only. Not very sustainable. That's the things. Renewable diesel. And then some is the total sustainable fuel. So they have the very strict requirements for the sustainable aviation fuel. That's why I make it different. Not only you able to produce the biojet fuel, but make sure the overall process. If not, they will categorize because they have the certain certificate agencies, certified agency. They are certified whether your process is totally clean or not, or whether your product is fulfill the requirement or not. Yeah, they have the certified. So yeah, this one is the current market that are facing. I take the examples in UK. In last year, you see total 141 million liters of the sustainable fuel has been applied. So you see, it increased almost double. I mean, we 45% increase in 2000 compared to the 2033. But 45% of the fuel sources are from the 0.4. Only 0.4 of the total are from the used cooking oil. So they are urgent need to have the reliable sources. We see because in UK they aim to have the how many percent? 1% or 2%? Yeah, 2%. The total amount that they need is what? 230 million liters. They only can produce 141 liters only. They want to have the around 2% to meet by 2025. 2025. But they able to meet 0.4% from the used cooking oil. So that's why it's very important to find sustainable sources or sustainable and reliable sources for the sustainable aviation fuel, because they already committed to have at least 2% by 2025. Then the challenge is what? To create a commercial scale of the sustainable aviation fuel production is need a billion of pounds. This one is UK scenario. A billion of pounds of investment. Yep. So they are also concerned of the supply. Supply wouldn't be able to keep up the demand. The supply of what? Supply of you see there are two main problems here. First is what? Very huge initial investment cost. Second thing, we are unable to find the sustainable sources. Yeah, sustainable sources. That's a thing. Yep. So if they want to increase by 10%, they need 1.5 billion liter by 2030. Because they already projected. So yeah, that's the thing. Facing by the current market. So this is the brief instructions there about the sustainable aviation fuel. Then now I want to move on to the our study. In this study, we want to determine what is the most optimum. For this study, is the exponential study or the very fundamental study to find the potential raw material that available in Southeast Asia. I can say it's a tropical country, I mean in Southeast Asia country, and what is the potential pathway that can produce the biojet fuel. I didn't say the sustainable aviation fuel first. So to get the biojet fuel, so we tried a lot of feedstock, a lot of the commercial catalyst without modify the catalyst. But the second phase, we will identify what is the sustainable raw materials or the resources that we can use. Then what is the targeted process and targeted catalyst can be used so that it can reduce the overall CO2 and CO during the process, and to get the qualities biojet fuel. So in this study, we want to see what is the effect of the different commercial catalyst, the effect of the catalyst rolling reusability. This one more on catalyst activities. The second is to determine what is the optimum the jet fuel hydrocarbon based on the palm-based feedstock with the different fatty acid profile. The fatty acid profile will affect the end product because I think last few days I mentioned to you they need the shorter carbon change because fatty acid profile can let you know what is the carbon change of the raw materials, and to determine what is the proper blending ratio of our product in order to meet the ASTM standards, or the ZA1 specifications, because we want to produce the biojet fuel that's as close possible to the ZA1 fuel. And lastly, we also do some preliminary study. What is the soot particles and also the particle size distribution of the different biojet fuel that we produce and brand. Whether it's already can reduce the emissions or not, can reduce the soot particle or not, the particle size can be reduced or not. This one, we do some preliminary studies about that. So based on the digital study, then we found that these fuel properties might be these fuel parameters might be affect the process of biojet fuel production. So that's why we are focused on what is the type of the catalyst using the type of the catalyst, and what is the types of the raw material, the feedstock we are using. Then see what is the blending ratios, the maximum blending ratios with the commercial jet fuel. Commercial jet fuel, we are choosing the ZA1 fuel so that it still can fulfill the biojet fuel requirements. So this is our scope. So we identify fuel, very common catalyst, 5 types of the catalyst with the loading, various percentage of loadings. Then the catalyst reusability up to 5 cycles, and see what is the effect. Then the feedstock, we identify 3 feedstock. 3 feedstock is also related to palm oil, because Malaysia we produce a lot of palm oil. One is the used cooking oil, but palm oil based used cooking oil, and palm kernel and palm orange oil. So we particularly see whether which one is more suitable, because we really need to see what is the suitable selectivities, and the blending ratios we blend from the 20 to 100%, with increase of every 20%. So for the fuel properties, we look at the chemical compositions by analyze using the GCMS, then the low temperature, fluidity and combustion characteristics, volatile, and also the rubricities of the fuel properties after that we produce. Then another quantification study is the soot particle size. We need to know what is the soot particle size. So this is the comparison because before we conduct we need to know to compare with other study. So this study we conduct in 2018. So that's why there are no any so there are more studies already appear here. So you see, just now I mentioned by using the hydropressing, we are using the hydropressing method. Hydropressing methods are from the oil-based or the fatty acid-based raw materials. So by comparing these all criteria of productions, so they some study they using a 1-step, 2-step, or even the 3-step. Nothing wrong and right. 1-step, 2-step, and also the 3-step. So we choose to produce by the 1-step. So normally people for the 1-step they using the deoxygenation or hydrodeoxygenation process with the hydrogen, or some of the study they are using the pyrolysis or even the co-pyrolysis. This one co-pyrolysis mix between the bamboo waste and also the microalgae. So they are able to produce the biojet fuel. So currently the biojet fuel that produced is relatively low yield. This one is not this one is the biojet fuel year and not consider the selectivity yet. Not consider the selectivity yet. So there are a lot of study about the hydrodeoxygenation process and also deoxygenation process. So they are using the model compound. They are using the model compound to see whether they can produce the green diesel or not. The green diesel or not, or jet fuel. Jet fuel, I mean the jet selectivity or not. From what compound they can produce, what type of the jet selectivity. So, but what we select here for our disease study only using the feedstock, I mean directly. Yeah, the model compound is good for us to refer whether we have this fatty acid. So what is the potential pathway, to convert into, or what is the potential reactions that can have if we have the certain reactions. Yep. But if we are using the feedstock, so there are many different compositions. So we don't know what pathway what we follow. So that's why some of the feedstock they have very long change of the hydrocarbon. I mean the carbon change. So at the end we might get the heavy. I can say the heavy biojet fuel, which the total density might be higher. So this is the some comparison. So our step is what prepare the feedstock and catalyst. You should set up the experiment, do the characterization, analysis of result and conclusion. This one is quite common. So this one, we are using the hydrodeoxygenation process without the pressure first. So this one is the fatty acid profile of the feedstock. Analyze the fatty. This one to analyze. This is not to produce the jet fuel first yet. This one to analyze what is the fatty acid composition only. To identify what is the fatty acid composition, we need to know what is the number of the carbon change. So after that, we activated the catalyst. So the reading here is we refer to the literatures based on what is the optimization catalyst activation conditions. We just use the follow the conditions. So because we want to just see what is the potential step. Yeah, this is the jet fuel production. So our aim is to explore and also figure out what is the potential feedstock. So we want to identify three best catalysts because we are using 5. Then aim to define 2 best pairing. Pairing is what we have 4 feedstock and 5 catalysts, which pair will produce the highest selectivities of the biojet fuels. Then after that, we will find the different catalyst loadings and also the brandings and also the reusabilities of the catalyst. You see of the catalyst. So we are using the nitrogen gas. This one is a condenser. So what we didn't measure here is the waste gas. The waste gas, we believe will produce some CO2 and CO because the pathway that we follow, the CO and the CO2 will be produced because we are using the hydropressing process. You see the process we are using is what? This one, the oxidation. This one, decarborization. These 2 process, the first 2 process is what we are using. So if we have the fatty acids plus the reaction, after the reaction, the jet selectivity will produce at the same time CO and CO2 will produce. So we believe that the CO and the CO2 is produced during the process even we didn't measure. Then after that, we will do the characterizations. As I mentioned, we are using the GCMS to measure what is the potential profile and also the selectivity, profile and selectivity, and to measure the viscosity. Viscosity is very important for the biojet fuel or the biofuel. And the other properties. And lastly, we also measure the rubicities and also the soot limiters to see what is the potential emissions we produce by using the biojet fuel. So after that is the analysis of the result. Okay, so yeah, I need to make it clear that the mass yield that we obtain here is the what? The total product. The total product, all the product. Liquid product here is what? We only select the jet hydrocarbon only. The jet hydrocarbon. So jet hydrocarbon. Then the jet paraffin selectivity is we just select the C between C8 until C16 only. So we measure these few things because we need to make sure what is the component or compound after we produce. So we not just take the total mass here because total mass here is not fair because some they have other impurity profile. So we just see what is the jet paraffin selectivity or the liquid product here. Yep. So yeah, this is the first set of the experiment. You see, this is the compound. That we produce. This is the compound that we produce. We have the N-paraffin, isoparaffin, olefin. This is all the what? The jet fuel selectivities. The jet fuel selectivities. But here we don't know what is the carbon chain yet. Because sometimes the carbon chain might be more than 16. 16. But this one is all the jet selectivity. Jet fuel selectivity. So this one make it what? Make it the composition in the liquid product. This one we just focus on jet selectivity. This one you see the total jet selectivity that produced is 60%, 50%, 50%, which the composition we have the N-paraffins and also the isoparaffin, olefins and aromatic compound. We also sort out the carbon that we have more than C16, yeah, the carbon more than 16. No, this one is the total mass. It's a total. This one is total. Yeah, this one is a total. So you see the WCO is waste cooking oil. But with brand name is what? Without any catalyst. This one WCO. with 5 types of the catalyst. So we found that they are the low catalyst activities, effect of the catalyst, or want to see the effect of catalyst. So this one we found that they are low catalyst activities by the basic catalyst of the CaO and also the titanium oxides. Due to the cake will be formed. This one the cake will be formed. And the zollite, vanadium, and also the barium carbons catalysts are the potentials to enhance the production of the jet fuel. Which one? Or this one have the higher vanadium. Let me see. This one without. This one without. Then the the mass is highest. The highest one. And they also have the highest N paraffin. Highest N paraffin. So these three. 1, 2, 3. These three are selected. So now we further studies that the effect of the different type of the pump-based feedstock, which we have the waste cooking oil. This one waste cooking oil is a pump-based used cooking oil or waste cooking oil, palm kernels, and this one is a palm olefin oil with different type of the catalyst. Compared with catalyst and without the catalyst. So we found that this one, the palm kernel oil, with the vanadium carbons and also the vanadium oxides, have the fair amount of the paraffin. We've maintained the low olefin yield and high mass yield, the high mass, which is more than 70%. So the lower fatty acid derived feedstock generally reduce the chance of the olefins for undergo the hydrogenation reactions to forming the N paraffin. So yeah, one thing you to bear in mind is, you see, what we found is we need to have the raw materials or the feedstock that have the low free fatty acid. Free fatty acid will have the negative impact on the overall productions. Here. Then after that, this one is a different loading catalyst because we found that this one is the best one. So we use these two sets to further study with the different loadings. We found that if the loading of the catalyst is go high, that means the total paraffin also higher, also go higher, which the total paraffin highest at the 8%. This one for the 8%. This one the paraffin. This one is almost similar. For this one is almost similar. So yep. This one 8% is the highest for the palm kernels by using the vanadium. Both also higher, they say, both also higher. With the lowest of the olefin. Yep. Then after that, we go to see what is the effect of the biofuel branding. Okay, so after that, we found that the 8% have the highest N paraffin. So we just take the 8%. The 8% one is yeah. This one. Let me see. Branding, yeah. Two type of the palm kernel. I think we take the 8%, then we brand with the various percentage. And this one is the Jack 100%. This one is the Jack A. Let's see which one is the 100%. Yeah, this one is a 100%. 100% Jack fuel. This one is 100% Jack fuel. So this one with branding. With branding with the different percentage. different percentage. So we found that blending at 20%, so the highest amount of the liquid product and lower olefins, lowest olefin. So we take the 20% to further analyze the properties, the various properties. You see the first property we analyze is what the density. You see we draw the two line here. Two line here is the SDN standard for the jet fuel, for the jet fuel, which must be the density must be lower than 0.4 gram per cm cube. Cm cubes must be higher than 0.75 75 gram per cm cube. So with all the branding, this one is a brand. Let me see which one is the branding. Oh, this one are branding with the. This one is a pure jet A1. So we have the two type of the biojet fuel. One is the using the palladium carbon, which is in the gray color, and also in the orange color is the vanadium oxide. So we found that most of the blending fulfills beside the what? Beside vanadium with pure biofuel. Then about the low temperature derivatives, which is the kinetic study. Use kinetic viscosity study. So the kinetic viscosity study must be lower than, I think, 1 point something or 2 mm cube per second. But you see, most of it will be more than that. Just 20% is slightly higher than that. Most of it is higher than that. So only the jet A1 fuel. So that's why previously I mentioned our viscosity is still slightly higher, which is we need to still reduce it, because the viscosity, higher viscosity will increase the molecular weight as well. So, and also the high viscosity will cause the ignition relay, and also will cause a negative impact on the atomization of the fuel spray, because the viscosity is very high for that fuel. So that's why. Then this one is the freezing point. Freezing point is one of the most challenging one, because basically for any type of the biojet fuel that we produce, we have the reactivity very high freezing point. So that is the part that we need to take care when we want to produce the biojet fuel, because reactivity. But after it's blending with the jet A1 fuel, it's still up to 20% for the this one. The palladium carbon one is also slightly lower than the bar. So that's why the second properties you need to take care is what the freezing point, because for the normal biojet fuel or normal green diesel, the freezing point that required is just a -10, but for the jet A1 fuel or for the biojet fuel, you need to have the -47. You don't have -47. So yep. Then lastly is about the calorific values. The calorific value. The calorific values must be, yeah, it's decreasing. Must be higher as well. So our benchmarking is around 46 or 47, 46 and 47 millijoule per kg. Millijoule per kg. What we get also slightly lower. So yep. So that's why we need to make sure you have the enough energy content per unit of the biojet fuel that you produce. Lastly is about the smoke point. So we found that in the biojet fuel, as I mentioned before, the biojet fuel generally have the lower smoke point compared to the fossil Jack A1. So you see this one is a Jack A1. They have the highest. So basically branding with the 20%. We will have the lower smoke point. Lower smoke point. So yep, basically this one is the expected result, because why? The biofuel generally have the lower. It can decrease with the carbon, or increasing with the carbon per hydrogen atomic. Yes, correct. Because why? Because the smoke from where? From your carbon. From your carbons. Yes. 80% is more processing. It means it's for the vending. Yeah, correct. So yeah. So we have to take the average point, because for the other property it's 20%. Yep. Then the lastly is the fresh point. Fresh point normally not a problem, because the fresh point normally it's the fresh point for the biofuel is relatively high. So the fresh point don't have any problem. Fresh point is due to what? Due to the storage and also the shipping and the transportation issue. But normally the fresh point of the biofuel is relatively high. So this is not the main issue. So the final blending point, the final boiling point. The boiling point is also the maximum limit we can have is 300 degrees C. But all the blendings are less than the 300. So this is not the issue also, because the final boiling point is what to make sure they have the complete combustions. So no formation of any deposits during the combustion. So that's why all the blendings are including the pure agent up to 95%. Yeah, of the biofuel at the lower boiling point. And lastly is the rubicities. The rubicities is what is able to help to improve the moving part. So we have to make sure the rubicities is up to the certain level, so that the fuel pumping and also the flow rate of the fuel moving smooth. So most of the blendings including the pure biojet fuel also have the desired rubicity, which is lower than the total requirement. The maximum requirement is 850. Yep. So then lastly is about the soot emission. This one also as expected, because the pure biojet fuel, or the pure biofuel normally have the lower emissions, have the lower emissions due to the incomplete combustion of the jet fuel and burnt hydrocarbons. Yep. Then after that we go to test the reusability, of these two type of the catalyst. We found that we are using the 8% of the loading. We found that it's up to 5 cycles. It's 5 cycles. The total production is still, the reuse still higher. But if compare between the vanadium and also the vanadium oxide, which the vanadium oxide have the better reusability, because why? You see, all is almost not any reduced in the total mass year. Not reduced in the total mass year. Yep. This one also same. I think both are also relatively have the similar result. They can quite stable, because why? This is the one of the commercial catalysts without any modification. So they are quite stable. They are quite stable catalysts. So our main findings from this study is what? We found that these two type of the catalysts, 5% and 8%. 5% is able to make the optimal amount of the jet hydrocarbons through the deoxygenation process for the waste cooking oil. Then the vanadium oxide catalyst have the better reusability compared to the vanadium carbons because of the jet selectivity of the vanadium carbon have the highest reducibility compared to the vanadium carbons. Then, but for the palm kernel oil, the liquid products can up to 99%, which they have the favorite selectivity, which is the palladium. Palladium selectivity is up to 73%. Both also 73%. Then this one also 95%. Then the acceleration of the palm kernel egg is optimum at 8%, which they can achieve around 70% of the jet selectivity. For what? Palladium selectivity for the alkanes with the least olefins. Yep. Then for the blending of the 20% is also fulfill the standard. Besides, there are two things almost in the borderline, which is the freezing point and also the viscosity. Freezing point and viscosity. So this is very important, two important properties that you need to make sure is reduced, can be reduced. So this is our finding. So our question here is why the sustainable fuel are not widely used in the market yet? Because of the price. What price? What price? Yeah. First is the production cost. Like you see, the second one is the production cost. We must make sure the overall production cost is as low as possible. At the same time, the price is what? Because the jet fuel, not necessarily any type of jet fuel is a significant for the total operating cost for the airline, any airline. That's why, because if we cannot maintain the cost of the sustainable fuel as compared to the jet airline fuel or the fossil jet fuel, so that's why it cannot be compatible to the fossil fuel. Because you see currently for the fossil fuel, it's around 600 euro per ton, but the current cost for sustainable aviation fuel is around more than 1,000 euro per ton, which is how many times higher? More than 50 times. Yeah, more than 50. More than 50, not time, percent. More than 50% higher. More than percent higher. So we need to make sure the sustainable aviation fuel must be as close as with the fossil fuel. Then one more thing is the fossil fuel. The price of fossil fuel also fluctuation. Sometimes go up, sometimes go down. If the fossil fuel go down, then how you need to make sure your sustainable fuel can be followed to go down as well. That is another challenges, you know. Yeah, that's another challenges. That's the thing. If you see because previously I discussed with you about the correlations between the fuel and also the food. If you're using the food sources or edible sources for the sustainable aviation fuel, if the fuel prices is decreased, fuel prices is decreased, so the farmer tend to turn the edible oil into the food, so make the overall edible oil might be increased as well. If you were to use that sources, that means the overall cost for the sustainable aviation fuel also increase. You know. Yeah. So that's the thing. So how you need to make sure the price is compatible. So now they can achieve through the incentive only. Because now it's the incentive because many countries they want to push for the sustainable aviation fuel. So that's what is incentive. Another one is the like you all mentioned is the production cost. So how we need to make sure the overall supply chain. We have the stable supply chain which we can get the sustainable feedstock that available and also the logistic because overall this sorting is not yet matured, because the current sustainable fuel is heavily rely on the incentive only. Incentive. Yep, that's the thing. So yeah. Oh, this one. If you want to know, if you want to know the overall production cost, you need to know what is the overall fixed stock and also the pathway for any process. So because before we start any process, we want to know whether it's economical feasible or not. So before that, you need to know what is the pathway for any type of the fixed stock and or any type of the process. Because later on, I will discuss about the overall life cycle cost analysis. Life cycle cost. So that's why we need to know this one. This one is the oil-based. For example, the oil-based fixed stock. So you go through the hydropressing of the ester and fatty acid method. So which I'm using this method. I'm using this method. Then we also have the sugar to jack. So what is the pathway they are following? Then another pathway that currently they are using is the gasification. I mean, industry are using is the gasification to produce the biojet fuel. So this is the quite stable and established process already, the fusion stroke process. So yep. So that is the pathway. So how you going? You can do the cost analysis through the process simulation. Because from the process simulation, you can know what is the major component or utility for each process. You know. Yeah, this one is process simulation is very important, so that you can save your time. To do the costing. So from the process simulations, you can know what the overall material and energy balance. So if you can know this one, then you can know what is the potential operating cost. So in order for you to do the process simulation, you need to have the data input. The data input is very important through the experiment or through the what. So that's why through the process simulations or the experiments, then you can have the input. Then after that, you can simulate what is the percentage of your output, what is the potentials product, and also the capital cost and operating cost, as well as what is the emission. Because why we have the energy balance. We have the energy balance. So the energy balance is shown very clear in the process simulation. For our group, yes. For me, for the process simulation, we use the Aspen Plus. Aspen Plus. Aspen Plus. So this one is promoting this simulation too, but this one is very good for the industry process simulation. Industry process, not only used for research, but also very useful for the industry's process simulation as well. But the license is very expensive. The license, there are two types of license. License for academic is relatively lower cost or affordable cost, but this license cannot be used for commercialization. Cannot use for commercialization if some company want to ask you to do the process simulation. You have that license, because your institute got that license, but you cannot use for that company. If you get caught, your institution, and you can get a very serious fine, you know. And this one must be, yeah. It's very worried. No. If you yourself own that software, then you can do for any country, any companies. If you are the consultant for that company, you own that license, you can do. Yeah, you can do. COMSO also. COMSO also another good process simulation tool. Yeah. So yeah, in our group we are using this one, but of course we are using the academic license. We didn't do for any commercialization. Commercial have the totally different license you can do. Yep. But this software or this tool is very good for the industry process simulation. So try to learn this one if you have time now, because why? In the future, when you work in any industry, you want to go back to industry, you want to do the consultant for any industry to improve their process. This is very useful. This software is very useful. Yeah, for any industry process, you can industry audit. If they want to see their carbon audit or emission audit also can. Can. Mainly the industry is used to improve their efficiency. Improve their efficiency so that they can reduce the overall cost. So identify. Then this is the costing. So this one is I obtained from one of the researchers from India also. He's already doing costing in Indian rupee. Then you see the overall cost is 113 per kg at this moment. 113. Then you see basically what the overall cost it come from what? Feedstock. The feedstock cost. The OPEX and CAPEX is almost similar. For me, I also do the costing also, but for me, I do for the biodiesel. Later, I'll show you how to do this one. How to do this one. I didn't do for the jet fuel yet, but I do for method are the same. Method are the same. So later on, I will show you my case study about that. So you see, overall, feedstock normally account 70% of the overall price. So if you can able to get one reliable, sustainable with low cost raw material or feedstock, you can make it. OPEX and CAPEX also relatively small. Then they have the hydrogen. They need the hydrogen. I assume he produced using what? Using the hydrodeoxygenation process. I believe because why? The hydrogen. He include the hydrogen cost as well. So what he predict is the overall cost. So you see, from here, what can you do? What can you do? You see, beside the feedstock cost, the cost of the hydrogen also relatively high as well, correct or not? So how are you going to get the low or sustainable hydrogen production as well? That's the thing. There's two things that you can do. Then the OPEX and CAPEX is also very low cost. This is what I told you. You see, we want to achieve net zero in 2050. Correct or not? You want to achieve net zero. I think most of you heard this term before. Net zero in 2050. So you see the emission is increasing year by year since 1990. Not to say since 1990. We have the data from 1990 because I show you before the 17th century already started the emissions. So you see it's already reached to almost how many emission achieved 1,000 million ton. It's almost same with what I show you last few days. Then this one during the COVID time, there are some reduced, right? Not. You see, if there are no any policies that control, you see, it will be increased in 5,200 metric ton. So if we do something with the additional efforts, so the overall the CO2 can be reduced to 2,000 metric tons from 5,000. 5,000 is the business as usual. This one I obtained from one of the aviation societies. So can be reduced from 5,000 to 2,000. But if we put in the more efforts, it can be achieved the net zero. So this is the gap that we need to close. and this is the gap that we need to close. So yeah, so because we want to have the carbon neutral growth in 2030, because it is our intermediate goal. The carbon neutral, that means what is compared to 2005, 2005. So there are no any increase in the what in the emissions, carbon neutral. So after that, to achieve the net zero, so that is a more much more effort we need to do. No, that one cannot. No, this one is the yeah. One more hour COVID. Yeah, cannot. It's not easier because you see the healthcare system or whatever. They also consume a lot of energy. They want the one we not consider, because now even the healthcare industry, they also talk about the sustainability, how to recycle, reduce the what the healthcare waste, Not only healthcare waste, they want to make their overall system sustainable. The procurement system, all those systems in healthcare sustainable, because the now healthcare industry is more profitable, right now, more profitable. Yeah, it's more in any country around the world, Yeah. So as a summary, we already achieved so much compared to 1990. Achieved so much. I mean, if this one without any policy, without any policy, if you are increased by this line, we already achieved so much. Fight today is what only half of the CO2 did in 1990. So all the sector industry are working the way to reduce the fuel use and also the emission further. Yep. So any questions so far? So I have another small slide to show about the life cycle cost to show you how are we going to analyze the life cycle cost. So before I continue, yes. Soot particles. Yep. Yeah. With your link to the earlier soot oxidation and higher particular rate. Aromatic. So this one, that means if we have the more aromatic compound, will lead to the overall soot will be higher. So that's why this one is we based on the compositions. We compare they have the high aromatic compound. So that's why they have the higher, lead to the higher growth. This is your question. Your question is what? Why lead to the soot? No. Soot happen is incomplete combustion. Correct now. Soot is not the CO2, Soot is is incomplete combustion. Your question is what? What? Oxidation. Yes. Higher particle. So now let me see. Will lead to the earlier soot oxidation and higher particle growth. This one I don't know what is the particle. Let me see. Oh, this one might be because they lead to the earlier soot oxidation, because they already oxidation, so lead to the incomplete combustion later on. Lead to incomplete combustion, so that's why the soot particle might be increased. Because they have the earlier ignition or earlier combustion. Earlier combustion, it means what? With a lack of the oxygen. Earlier combustion is lack of the oxygen, so that's why. Yep. Yep. Any other questions? If not, now I will share another. Right? Is the life cycle, the life cycle cost. This one I take the case study in Malaysia, because last few days, last 2 days, one of your participants or some of the participants asked me to show what is the techno-economy analysis. So I use this one as a benchmarking study. So all the techno-economy analysis or the economical feasibility share the same methods. Share the same methods. So at the end, you can get this type of graph. Yep. This type of graph. So what is the total life cycle operating cost for the certain project up to? It's up to you. You want to put how many years? This one they put 30 years. 30 years. The total 30 years. For my case, I put 20 years. 20 years. The lifetime of the plant is 20 years. Then for us, we make few step forward. Few step forward. I mean, you see. So my time is until what time? I need to. 10-15 minutes. Okay, I just quickly show you something. Show something. If not tomorrow, I will show you. You see, yeah. This one I didn't break down only. So in this study, this one is the same thing. I just didn't put in the proper breakdown the cost only. Break down the cost per unit. This one is the total cost per unit. I show or not? I didn't show. Oh, this one I break down. I didn't. So you see, in this one, I show the life cycle cost for 3 type of the freezer, bar and calofilm type of the biofreezer for a lifetime project lifetime of the 20 years. So this including the overall initial investment cost, the operating cost, the feedstock cost, all the costs for the lifetime of the 20 years, which are including the discount rate. Discount rate is what you know. Discount rate, this one is very important. So many people are doing the life cycle analysis or the cost analysis. They ignore this one, Anyone know what is the discount cost or the interest rate cost? Change for this country, but why we need to consider? Some of them they call the discount cost or the interest rate. Why? Correct, inflation. Because the $100 today maybe worth $90 for the next year. Only so that's why it is very important to consider the discount rate in your life cycle analysis. If not, it's not fair. Because for example, after 20 years, you still assume this is $100 is not fair, because you didn't consider the inflation. So that's why in our study we also consider the discount rate. So of course, when you want to do this life cycle analysis, you need to know all this data input, from where the data input come from. First, if you have any plan to refer, you can get from there the input. And second, from your experiments, you upskill it, then you can know, because we need to know the properties or the properties, and also the years, the purities or everything from the real data that you want. And third, from the simulation that I show you, the simulation data. So normally what we do, after we conduct the certain experiments for the certain technology, then we are running simulation to verify back with the experimental data. After do the simulation, with the simulation data, it's very easy for me to do the costing analysis as well as the emission analysis, which is we call the life cycle analysis. It's very simple and easy. So from this one, you see, we can break down. Same thing, the fixed stock cost, how many percent. This one I just break down in this way. The maintenance cost, operating cost, capital cost, and also the byproduct credit. Because why? Biodiesel produce the gas oils as a byproduct. Then that one is the sales value is what? After end of the 20 years, the value of your asset. The value of the assets. This one I consider all. So this one, this all costs. Then from here, we can calculate the payback period and also the unit cost from here. Unit cost. So you see, similar. I get the almost similar result. You know, the fixed stock cost is 80%, 70%. Same for biofuel. Cannot run away from this one. Yeah, cannot run away from this one. That's the thing. That's the thing. Cannot run away. So you see, this one I conducted 15 years ago. This one because now I still doing the costing, but I don't have the slide to show you. You can refer back to my papers. Recently I have a few papers also doing the costing and also life cycle analysis, but I didn't do the slide. This one is 15 years back, still the same. You know, the feedstock cost is the highest for the biofuel, biodiesel, especially. So what we can do more is do the sensitivity analysis. This one I do one step forward. The sensitivity analysis. Why? Many price are changed, fluctuations. For example, the crude oil price. If the crude oil price is changing, what is the impact? So what is the impact? So if the discount rate is changing, maybe sometimes the inflation is too high. So what is the impact? The positive or negative impact? Oil conversion year. If the technology is keep improving already, you get the higher rate. Or the operating rate, the operating cost. Maybe you can minimize the operating cost. So what is the effect? This one you can do. This one. So you see, normally, what we found, one thing, the initial capital cost is relatively small. I tell you, very small. For any business, I think who are doing the business, you know, right? Yes, the initial capital cost you think is very big, but overall, after that you see the overall cash flow. You have found that the initial cost is relatively very small. Any business also same. I tell you, compared to the cash flow and also the initial capital cost, they are initially very small. Then really have very small impact. You know, small impact. This one is the three type of the biodiesel, and also what I do, I also do if the crude price or any price changing. So what is the production cost? So that you know. Then the horizontal line is our current diesel cost. Of course, I do this one is based on the Malaysia scenario. Every country have a different scenario. That is the cost. So we also do the potential CO2 can be saved, the life cycle analysis. Yeah. So what is the total component that we need if we want to run a certain amount of the biodiesel, replace a certain percentage. This one, another interesting thing. Draw a line. What is the price of the crude petroleum or the crude oil price versus the crude oil price? If for example, if the crude oil price is increased up to 125, then the crude palm oil price is maintained at 500. Saving can be generated. Saving can be generated. Then if the palm price remain at 1,000, then your crude palm price is 100 per barrel. Then the crude palm price is 1,000. I mean, subsidy is required if we still want to use the biodiesel. This is what we are doing. Yep. So. No, it not necessarily. It's not necessarily. Sometimes, look from this chart, you can see very clearly. If this grow and then that grow until what time? What is the price? then you cannot take it anymore. Yeah. This one, the saving generated, I mean you can assume that this is the profit that you can have. This one is maybe the margin, then the loss. Yeah, it's a one can be changed to any fixed stock price. The concept is same. The concept is same. Then this one can change to the maybe the Jack A1 price, example. This one is your fixed stock price, for example. Yeah. So yeah, this one I don't have time to show you in details. Yeah. Yeah, this one. So any other questions about that? Costing analysis. For the biofuel, no. At this moment, we don't. The production cost for the biodiesel is almost. They can get the profit. They still can get the profit. Yeah, at this moment. So, but during in 2010, 2010, because during that time, the crude palm oil price is relatively high, and also the crude oil price is relatively low. Many factors goes down during that time. Yeah, during that time. So now leftover, they still can survive. Now, because Malaysia, we already have the mandate that we need to use 10% of the biodiesel. Yeah, previously you want to increase to the higher rate. So many others issue like what I mentioned before, the car manufacturers, they don't want to have the car warranty or whatever if you are using more than certain percentage. Car manufacturer, car manufacturer, this one, and many other things. Yeah, it depends. No, right? We don't have. Initially we have, but now we don't have. Now we don't have. The subsidy normally is provided during the very beginning of the policies only. Very beginning. Yeah, very beginning. Yep. So any other question? If not, I think that's all for today. So yeah, thank you.
So thank you, sir. Thank you for the session. And for now, we'll call it a break. And now we can go for lunch. So post lunch from 2 o'clock, we will have lab visits. So first of all, we will be going to the pilot scale laboratory visit. So since the pilot scale laboratory visit cannot accommodate all at once, we'll go in batches. So first batch will go visit the pilot scale reactor and go to the School of Infrastructure Environment Laboratory. Then the second batch will follow the same route. So in the SIF, like School of Infrastructure Environment Laboratory, all the batches will go at once, visit the laboratory at once. But the pilot scale, it will be in batches. It's fine. So from 2 o'clock onwards, the lab visit will start. So I request every participant post lunch, please be seated over here so that we can easily accommodate all the participants for this lab visit. Thank you.